Hello again, and welcome to the first of a series of lectures devoted to developing formulas for calculating derivatives. You'll remember from last time we developed the formula for a derivative and did some examples using that limit definition. It was based on the tangent line problem that we did back in Lecture 1. And I think you'll agree with me that that computation using that limit definition is pretty difficult. It often requires a lot of algebra. We also saw some examples of functions that did not have a derivative at a certain point. The key example here to carry around with you is the absolute value function, that V-shaped curve. It does not have a derivative at x equals 0 because there's a sharp point there. Being differentiable, having a derivative, means geometrically that you're smooth at that point and don't have a sharp corner or what we like to call a cusp. So today we're going to develop a series of formulas for calculating derivatives in which we avoid using that difficult limit definition. I think you'll discover that these formulas are very easy to use with a little bit of practice. Before I get going, though, let's recall that definition of derivative with the limit definition. F prime of x, that's our notation for the derivative of f of x, or the notation dy dx, which reminds us that the derivative is dealing with change in y over change in x. And it's the limit as delta x goes to 0 of f of x plus delta x minus f of x, all divided by delta x. So remember, this is basically the tangent line problem. We're talking about change in y over change in x and then taking a limit. So let's start off with perhaps the easiest formula for calculating the derivative, and it says that the derivative of a constant function is 0. Well, does that make sense? A constant function like y equals 7 is a horizontal line. What would you expect the slope of a horizontal line to be? 0. So that's the derivative of a constant. So notationally we write the derivative of c equals 0. Now, there's a formal proof of this, and of course it would use that limit definition. You can see it in any calculus textbook, and it's not a difficult proof. But I think geometrically you believe it. The derivative of a constant is 0. For instance, here's a set of 4 functions. Let's calculate their derivatives. How about y equals 7? The derivative y prime would be 0. F of x equals 0. The derivative f prime of x would be 0. S of t equals 4. Notice I'm using some different letters here. T now is playing the role of x. And in this case, s prime of t would be 0. How about y equals 3 pi squared? Don't be fooled, 3 pi squared is still a constant, isn't it? So y prime would again be 0. Then we have another very important rule, the power rule. And it says the following. If you have a function f of x, say, equal x squared, or x cubed, or x to the 5th power, or x to the minus 2 power, x to any power, its derivative is very simple to calculate. It's nothing more than the power times x to the power reduced by 1. More formally, f prime of x would be nx to the n minus 1, where n was the original power. The derivative of x to the n, well, here's how you do it. You bring the n down into the front, times x, and then you drop the exponent by 1. We saw this formula actually used earlier. Remember when we did the derivative of x cubed and we used that limit definition and discovered the derivative was 3x squared? Well, that's how the formula works. X cubed, you bring the 3 into the front, and then the power was 3, and you drop it by 1, so it's 3x squared. Pretty simple, isn't it? Let's do some examples using the power rule. For example, what's the derivative of x squared? Well, it would be bring the power down, 2, times x to 2 minus 1 power. I'm dropping the power by 1, so it would just be 2x. By the way, we looked at that function, x squared, back in lecture 1 when we found the tangent line. Remember, we asked what's the tangent line's slope at x equals 2? Well, now we know how to do it. Take the derivative's 2x, plug in 2, you get the answer 4. And that's the answer we had way back in lecture 1. How about the derivative of x to the 2/3? The same rules apply, even though it's a fraction. It would be 2/3 times x to the power 2/3 minus 1. Oh, we're getting some exponents here. I know, a little rough going. So it's a 2 in the numerator, the 3's in the denominator, and it's x to the minus 1/3, which is equivalent to x to the 1/3 in the denominator. So the final answer is 2/3 times x to the 1/3. By the way, what happens at x equals 0 here? Is the function x to the 2/3 differentiable at 0? No, because you can't divide by 0 in mathematics, and the derivative would be 0 in the denominator at x equals 0. How about the derivative of x? That's pretty simple. Well, the formula, that's x to the first power. So you would bring the 1 out in front, and then it would be x to the 1 minus 1, and x to the 0 is going to be 1. Anything to the 0 power is 1. And so the final answer is 1, and we expect that because the line y equals x is a straight line of slope 1. So its derivative is 1. How about 1 over x squared? What's the derivative of 1 over x squared? Well, that's the same as the derivative of x to the minus 2, and then you use the formula, minus 2x to the minus 3. And then bring the x to the minus 3 down to the denominator, and you have minus 2 over x cubed. Pretty nice stuff, isn't it? Let's look a bit closer about some of the geometry of one of these examples. Let's look at x squared, whose derivative is 2x. And let's analyze what that means about the graph of x squared at various points. For instance, what's the derivative f prime at minus 1? Well, you'd plug in minus 1 and get minus 2. That means at minus 1, the slope is negative. The graph has a tangent line that's going downwards. How about at 0? What's f prime of 0? That's 2 times 0, or 0. So the curve is flat there at the origin. And how about f prime of 2? That's 4. You might remember that answer from lecture 1. Here's a picture of x squared, and you see that I've indicated the 3 points whose derivative we just calculated. Notice that the function is decreasing at minus 1, and it's increasing at 2, and it's kind of flat at the origin. Okay. What's our next rule? This is called the constant multiple rule. It's very, very simple. All this says is, if you're taking the derivative of a constant times a function, you can do the following. Multiply that constant times the derivative of the function. That's all you have to do. Let me show you some examples. How about if y is 2 over x? Let's calculate the derivative of that function. So I'm interested in the derivative of 2x to the minus 1 power. Notice I'm using properties of exponents to move the x in the denominator up into the numerator. And now that 2 in our brackets can come outside the derivative sign, because this is the derivative of a constant times a function. I can pull the 2 outside and just differentiate x to the minus 1 by the power rule. And I get 2 times minus 1 x to the minus 2, and then I simplify that result to be minus 2 over x squared. Trust me that as we go along, you'll be able to use this constant multiple rule very naturally, and you won't even think you're using it after a while. Here's another example. How about the derivative of the function 5 times the square root of t, and now t is the variable. Well, that's the derivative of 5 times t to the 1/2. Pull the 5 outside, and you get the derivative of t to the 1/2 is 1/2 t to the minus 1/2, and then simplify that result with some algebra, and your final answer is 5 over 2 square roots of t. Let me show you a more complicated one. Complicated because the pre-calculus is difficult, not because the calculus is difficult. Suppose you have the function 7 over the quantity 3x to the minus 2. Well, strange looking problem. Well, that minus 2 exponent really means that 3x is in the numerator. And when you square 3x, you get 9x squared. So this function is really 7 times the quantity 9x squared, which is 63x squared. And the derivative then is 63 times the derivative of x squared, which is 2x. So it's 126x. Good. I hope you agree with me that this is a pretty easy formula to use. Let me show you some other easy ones. The derivative of a sum of two functions. Fortunately, that's the sum of their derivatives. And the same with the difference of two functions. So it's very easy to calculate, say, the derivative of a long polynomial. You just differentiate each piece one by one. The derivative of a sum of any number of functions will be the sum of their derivatives. We like to say in mathematics that differentiation, finding derivatives, is linear because it respects summations like this. Let me show you some examples of this. What's the derivative of the polynomial x cubed minus 4x plus 5? Well, all you have to do is differentiate each piece and add them up. What's the derivative of x cubed? 3x squared. What's the derivative of minus 4x? Minus 4. What's the derivative of 5? 0. It's a constant. So the final answer is 3x squared minus 4. How about the derivative with respect to t of the function 3t to the 5th minus 14 pi? Well, the derivative would be, do the first term, and that will be 15t to the 4th. Notice how I kind of did that in one step. I'm really doing the following. I'm differentiating t to the 5th, which gives me 5t to the 4th, and then multiplying that 5 times 3 to give me that 15. But as you practice this, you'll do all of that in your head. And then, of course, the second term is a constant, so its derivative is 0. Good. So we've seen the derivative of a sum and the difference and the power rule and constants, etc. What about the product of two functions? What about the derivative of a product of two functions? Well, it's sad to say, I'm sad to say this, it's not the product of their derivatives. Be very careful here. The derivative of a product is not the product of derivatives, nor is the derivative of a quotient of two functions the quotient of their derivatives. The formulas for products and quotients are a little messy, and we'll do them next lecture. So just hold on and we'll talk about that next time. Okay, what about our friends, the trigonometric functions? Are they going to have derivatives? Of course, everybody's going to have a derivative here. Let's look at two formulas for sine and cosine. It turns out that the derivative of the sine function is the cosine function, and the derivative of the cosine function is the sine function. With a little caveat, it's minus the sine function. And that's very unfortunate that there's a minus sign that jumps into the formula here. As a teacher, I always forget which one has the minus sign. Is the derivative of sine cosine or minus cosine? And the same with the other formula. And you've got to memorize this. That's the bottom line. You have to memorize it. And I admit, I'll be very honest, it's really sad that there's a minus sign in the formula for the derivative of the cosine. But just memorize this. That's just the way it is. I didn't invent calculus. The proofs of these two formulas are in any calculus text. And in particular, the formula for the derivative of the sine uses that limit we talked about of sine x over x as x approaches 0. Remember that limit? That limit was equal to 1. Let me also look at the graph of the sine function. Here it is. And talk about what that derivative formula tells us about the graph. So the derivative of sine is cosine. Okay, so what's the derivative of sine of x, say, at the origin, at x equals 0? Well, it would be cosine 0, and cosine 0 is 1. What does that tell me? That tells me that at the origin, the slope of the sine curve is 1. So what's the tangent line to the sine curve at the origin? Well, it's the line of slope 1, and it goes through the origin. It's the line y equals x. Isn't that interesting? The sine curve and the line y equals x are very close to each other at the origin. Y equals x is in fact the tangent line to the sine curve at the origin. I mentioned this earlier, that when x is really small, x and sine x are close together. You can verify that on your calculator. Take a small number, calculate its sine, and you'll get basically that number back with a slight round-off error. Let's do some more examples using our new formulas for the derivatives of sine and cosine. How about the derivative of 3 sine x plus pi? Well, it would be 3 cosine x plus 0, because pi is a constant. That's pretty simple. How about the derivative of 5x squared plus 1/3 cosine x? Well, the derivative will be 10x, that's using our power rule with that constant 5 in front, and then the derivative of cosine is minus the sine, and the 1/3 is just a constant, so it's minus 1/3 sine x. You'll have a chance in our workbook to practice a lot more problems of this style until you get very comfortable with it. Trust me, it's not too difficult. One reason I know it's not too difficult, most graphing calculators now have these formulas built in, that you just put your function in, push a button, and out comes the derivative. Let's look a little bit now at rates of change. You can think of the derivative as being a rate of change. It's the rate of change of y with respect to x. That's the quotient. But we can also do, for example, the rate of change of position with respect to time. So we'll use s of t to be the position of a certain particle. And s of t plus delta t would be the position at a new time, say time t plus delta t. Remember, delta t will usually be a small number. The average velocity between times t and t plus delta t would be the difference in the position, so it would be s of t plus delta t minus s of t, all divided by delta t. In other words, it's the change in position over the change in time. Well, what would the instantaneous velocity be? That would be taking the limit as delta t shrinks down to 0, and you get the following formula for velocity. It's the limit as delta t goes to 0 of the numerator is s of t plus delta t minus s of t, and the denominator is delta t. Do you recognize that formula? Yeah, that's the definition of derivative with just some different letters, just to confuse us. But that's the definition of derivative. That's s prime of t, or if you want, ds dt. Let's do an example. If you have a free-falling object being influenced by gravity, assuming no air resistance, then there's a formula from physics which says that its position is 1/2 gt squared plus v sub 0t plus s sub 0. Now, in this formula, here are the characters. S sub 0 is a constant, and it's the initial height of the object that I'm, say, dropping it from. Boom, it drops down. V sub 0 is the initial velocity. I might be throwing the object down, and then it'll have an initial velocity. Or I might be throwing it up in the air, and it'll have an initial velocity in the opposite direction. G is what's called the acceleration due to gravity. It's a constant, and on Earth, it's approximately minus 32 feet per second squared, or minus 9.8 meters per second squared. Good. So once we know this position function, and by the way, you should probably memorize this because you'll see a lot of applications of this model in calculus courses. Its derivative, the velocity of our particle, would be, well, I'll take the derivative of the first term. That will be gt, because the 2 and the 1/2 cancel. And then I'll get the derivative of a constant times t is just that constant, v sub 0. So the derivative is gt plus v0. Let's do an application. So I'm in my swimming pool here, and I'm diving off from a platform. Let's assume the platform is 32 feet high, kind of a scary dive, and that I jump up in the air with an initial velocity of 16 feet per second. Then my model would be, for my position in this dive, would be minus 16t squared plus 16t plus 32. The 32 is the initial height. The 16 in the middle is the initial velocity. And then the 1/2 gt squared in the front turns out to be minus 16t squared, when you do the arithmetic using the g, which was minus 32 feet per second squared. So let me ask the following question. When does the diver hit the water, according to this model? And how fast is the diver going? What's the diver's velocity when the diver hits the water? Well, let's do some arithmetic. The position function was minus 16t squared plus 16t plus 32. Let's factor out a minus 16, which leaves a polynomial, t squared minus t minus 2. We set that equal to 0 and factor it, so it's 16 times t plus 1 times t minus 2. Hence, there are two values of t, but I want the positive value. That'll be 2 seconds. So the position is 0 after 2 seconds, so that must be when I hit the water. What's my velocity when I hit the water? Plug 2 into the velocity formula, which was minus 32t plus 16. You plug 2 into that, you get minus 32 times 2 plus 16, which is minus 48 feet per second. That's a pretty large velocity in the negative direction. I'm going down. We've developed so far many, many rules for calculating derivatives. And I think you agree with me that they're pretty easy to use. But unfortunately, or I like to say fortunately, you still can't get away from needing the original definition of derivative in some examples. Let me show you a very simple looking function whose derivative is pretty hard to calculate without using the definition of derivative. It's a very interesting function. I think you'll like the graph of this function too. The function is x times the absolute value of x. X times the absolute value of x. And I'm going to ask the following question. What's the derivative at 0? Now, we don't know. Our rules don't work here. The main reason being, we've got that absolute value. And remember that at 0, the absolute value function doesn't have a derivative. But maybe x times absolute value function does have a derivative. We'll find out in a moment. Of course, if x is positive, there's no problem. This function is then just x squared, because the absolute value of x would be x, and the function is x squared, and the derivative would be 2x. That's easy. And if x is negative, it's also very easy. The function would then be minus x squared, and the derivative would be minus 2x. So I know the derivative everywhere except at 0, and I still don't know if it even has a derivative there. Well, let's do the computations. Our function is x times absolute value of x. I want to calculate the derivative at 0, which is the same as calculating the slope of the tangent line at 0. Is this function smooth there? Does it have a tangent line there? I'm going to use the following limit definition of the tangent line, which is equivalent to the definition of derivative. It's the limit as x gets closer and closer to 0 of f of x minus f of 0 over x minus 0. Remember, this is change in y over change in x. Okay, let's plug in the characters. f of x is x times the absolute value of x. F of 0, of course, is 0. And x minus 0 is x. So we have the limit of x, absolute value of x, all divided by x. Cancel the common factor of x, and you're left with the following limit question. What's the limit as x approaches 0 of the absolute value function? That's no problem. The absolute value of x approaches 0 as x approaches 0. So that limit is 0. Isn't this kind of weird? The absolute value function does not have a derivative at the origin. But this function, x, absolute value of x, does have a derivative at the origin, and that derivative is 0. Now, let's verify with a picture. Here is a graph of x, absolute value of x. This is really a neat graph, I think. For instance, if x is positive, the graph is nothing more than x squared. And if x is negative, it's negative x squared. And at the origin, at 0, that was the problem child, 0. At 0, this curve is flat. It's got a derivative of 0. It kind of looks like x cubed, doesn't it? But it's not x cubed. What it really is, it's x squared with the left-hand portion flipped across the x-axis. But this curve is smooth. It has no sharp corners, and hence it's differentiable everywhere. And in particular, the derivative at 0 is 0. Nice. Okay. Let's look at sort of a problem that actually leads to some skills that will come up a little bit later in the course. Where does the graph of the function x cubed plus 3x have a horizontal tangent? Well, now let's make sure we understand what's going on. This function has a graph. I don't know what it looks like yet, although I'll show you a picture in a moment. I want to know if it ever goes up, say, and then has a tangent line where the slope is 0, horizontal tangent. Is the slope here ever 0? Or in our derivative language, are there any points on this curve where the derivative is 0? Well, let's take the derivative. The derivative is 3x squared plus 3. Notice how fast I did that. 3x squared plus 3. Is that ever 0? It's never 0 because it's 3x squared, which is non-negative, plus 3. Here's a picture of that curve. And notice it never has a horizontal tangent. Contrast that with the function x cubed minus 3x. Aha! Does it have any horizontal tangents? Let's take its derivative, 3x squared minus 3. Well, now I can factor this. I can set it equal to 0. It's 3 times x minus 1 times x plus 1, and that's equal to 0 when x is 1 and minus 1. Here's a picture of that graph. See that it has 2 points where the tangent line is horizontal. These will play a big role later on in this course. We'll identify those points as being little local high points on the graph or a local low point on the graph. They'll play a big role in applied mathematics. So, we're through or finished today with a set of fairly simple rules for calculating derivatives. The downfall was we saw an example where we actually still need to know that formula. Next time we'll look at that question of what's the derivative of a product of two functions or a quotient of two functions. For instance, suppose you had to calculate the derivative of, say, x cubed plus 5 all divided by x squared plus 3. Up to now, we don't know how to do that problem. And the formula for calculating that derivative is not as nice as we'd like it to be, but that's what calculus is. Again, I highly encourage you to practice some of the exercises in today's lesson in the workbook, because they'll give you a lot of practice on using these formulas, and then you'll be all set to attack the product rule and the quotient rule next time. So thank you very much, and I'll see you next time.